So on to page 36, we have cases that involve initial conditions. So this goes right back to the beginning of the packet. When you're finding a solution to a differential equation or a definite integral, an indefinite integral, you have that plus c on at the end. So it's a question of, well, do I want the general solution or do I want the particular solution? The tech assignment that's due next week, I sent out a video tutorial on that today. It's very, I think this one is as straightforward as you can get. So don't wait to get started on that one, but you should get a lot out of it because it really kind of drives home the idea of a general solution versus a particular solution. So it ties in nicely with what we're doing in class. All right, it talks about slope fields and things like that too. All right, kind of stuff that you never really have time to dive into in class, but it's a perfect opportunity for a tech assignment. But anyway, if you have a condition that allows you to solve for the actual value of c, and so that's what we're going to do here. It's just, dang it. Where? I don't know where my brain is sometimes. Oh, no. Actually, I know exactly where it is. Okay. I was like, wait a minute. Because I'm looking at 11 and 12. I'm like, those are just rules. But I intend to show you how to use substitution to figure those out. All right. So my brain is right where it is. It just is what it is. All right. So we're going to set up our solution here. So f of x is going to be equal to the antiderivative of secant squared 2x dx. All right. Now we'll worry about the condition in a second. Now you look at this one and you say, okay, well, what do I do? Do I let secant be my u? Do I let the 2x? Do I let secant of 2x be the u? It's really, dealer's choice when it comes to deciding initially. But this goes back to what I was talking about before. If you know your rules, then you're already ahead of the game. Because the derivative of tangent is equal to what? Secant squared of x. All right, so I already know that if that 2x wasn't there, I would have the antiderivative already. So what I want to do is replace the 2x with a u. And then differentiate. Du equals 2 dx. Now looking at my integrand, I don't have a 2 in there. Right? The u is going to replace the 2x. I don't have a floating 2 to get rid of, so I'm going to solve this differential equation for just dx. Right? So 1/2 du would be equal to dx. So you're just applying a little bit of algebra here. That's going to, and I mean a little bit, that's going to replace this guy. So we're looking at secant squared of u and then we have that 1/2 du. All right, so it's just a question of where do I want to put the 1/2? Inside the integral, outside the integral, it doesn't make a difference. I'll put it inside. All right, so yeah, this is going to be 1/2 tangent u plus c. But since u is equal to 2x, that gives us our general solution, f of x equals 1/2 tangent of 2x plus c. And honestly, I should have picked up on that one way earlier. Because the minute I wrote f of x and then I proceeded to write an equation that had u in it, that should have been like red flag. we got a problem here. So, but it didn't happen. So anyway, now we could do the substitution. It's going to be 2 for the y is equal to 1/2 tangent. I'm multiplying 2 by pi over 2 because the x value is pi over 2. So 2 by pi over 2 is pi. And what is the tangent of pi? 0. All right, so 2 equals c. And so that's going to give us what I was desperately trying to force to be the right answer before. 1/2 tangent 2x plus 2. All right, and that's our particular solution. All right, so as this compares to what we were doing before, you can see really, I mean, it's the extra step. I mean, granted, you have to do the extra step correctly. That's a me problem, not so much a you problem, but that's really what it comes down to. The idea that you're not just leaving it in terms of c, you're solving for the particular value of c that satisfies the condition that was given to you. All right, pi over 2, comma 2. A nice, easy way of checking this, and it actually couldn't be any easier, would be to put your function in your calculator and just test to see if pi over 2 comma 2 falls on that curve. If it does, then, I mean, unless you made like a slew of offsetting mistakes that somehow got you to the right coordinate, odds are you did it correctly. All right, so you just type this f of x, the particular solution in y1, and then go into the graph and select value. Value is a good feature, and then just pop it in that way. I can show you real quick. Do a lot of hand waving when it comes to that, but let's see if I can actually put my money where my mouth is. Like, just do it this way. It's so easy. Oh, the glare. Wait, now it doesn't want to show. I don't get it. Okay, so undo. Is take you through number 11, and that'll give you a little blueprint on how to handle number 13, which is a pretty interesting problem. Now there's a rule for it. Actually, I said 13, but I meant 12. And honestly, I might have to take you through both because I don't know that you'd necessarily come up with the approach.
Ours is 13.
Your 11 is on 13.
Yeah, so there are 2 allotments with that one.
Oh, that must be because I caught a typo quickly enough to fix it for yours, but I must have uploaded this prior to fixing the typo. But I'll still take it. If somebody wants it, I'll take it. Because I still should probably fix this, because this should be 13 and 14, right? Oh, yeah. Yeah, that's how I'm extraordinary. I don't make normal mistakes. I make extraordinary ones. So we have to pretty much do the same thing, but by finding the antiderivative of the tangent function. So f of x is equal to the antiderivative of tan x dx. All right, so the question might be when you look at this, all right, well, I struggle to see how u substitution plays a role in this. But maybe if I write it like this, it becomes a little clearer. All right, now, tangent is one of the 6 trig functions, SOHCAHTOA and the other 3. So technically, you could just memorize the rule, but it's nice to know where it comes from. Right. So what we're looking at here is a case where I can go in a bunch of different directions. Maybe I'll let my u be equal to the sine of x. Well, a bunch of different directions. I can go in two directions. I can let u equal the sine of x, or I can let u equal the cosine of x. Right? What you want to do when you're defining a u is choose a u so that when you actually incorporate it in, it simplifies things. You want it to clean up your integrand. All right? If I replace the sine with a u, that's fine. It's not bad. But I now have a cosine as a denominator. Do I want that? Well, generally I want to avoid having trig functions in denominators, because what that means is that I'm dealing with a reciprocal trig function. All right? Cosine on the bottom is the same as secant. So I don't want to deal with that. So my gut is taking me in the direction of letting u equal the cosine. And just as a general rule of thumb, if you have a choice, if it comes down to it, u as a numerator or u as a denominator, make it the denominator. All right? It's going to make things a lot nicer. So du is equal to negative sine x dx. Well, I don't need a negative. So negative du is equal to the sine of x dx. All right, so there's my substitution. I have a direct substitution. So sine of x dx gets replaced with the negative du. And on the bottom, the cosine of x, well, that's just a u. That's what we defined it as. So I can clean this up and make it negative 1 over u du. Now you might consider writing it as u to the negative first, but I prefer to write it this way because this is the result of a rule. The derivative of what? ln. So we're looking at negative ln of u. All right? Absolutes. All right? We include absolute values because the cosine function can be positive or negative, right? But you can't take the log of a negative number. So I need only the parts of cosine. I mean, once I do the reverse substitution, I need only the parts of the cosine that would be positive, right? So reverse substitute. So negative ln of cosine of x plus c. So that's one way to represent your antiderivative. Another way to do it would be to take that coefficient, properties of logarithms, take that coefficient and swing it on up and make it the exponent. So ln of cosine of x raised to the negative first power. What's cosine of x raised to the negative first power? AKA, what's the reciprocal of cosine? Secant. All right, so that's my general solution. Either one of those are technically correct. Actually, any of these three variations are all technically correct as the antiderivative of the tangent function. Negative ln of cosine, ln of cosine to the negative first, or ln of secant. They're all equivalent. But one of them looks cleaner than the others, and that's the secant one. All right. It's just people kind of shy away from the reciprocal trig functions because, you know, you're not as comfortable with those sorts of things, but they're not something to be shied away from because you should familiarize yourself with those because it makes life a lot easier. In fact, when we get into inverse functions, and we still have to figure out what C is here, when we get into inverse functions, you'll see that the three most important trig functions are not sine, cosine, and tangent. It's actually sine, secant, and tangent. In fact, anything with a co attached to it is an offshoot of something that doesn't have a co attached to it. So if you know everything there is to know about sine, then by extension you know everything there is to know about cosine. Same thing with tangent and cotangent. Same thing with secant and cosecant. All right, so the three most important functions are sine, secant, and tangent, except there isn't a fun mnemonic device for Shatoa. Shochakao, yeah. Yeah, that's for all the reciprocal ones, yeah. Yeah, it sounds fun, but it didn't quite catch on quite like Sokotoa, you know. But it's pretty important. So we have f of x equals that. Now our condition is f of 0 is equal to 3. 3 is equal to ln of the secant of 0 plus c. So I just need to know what the secant of 0 is equal to. Or I'll take the cosine of 0. 1. And since secant is a reciprocal of cosine, it's also 1. So then I would ask what the natural log of 1 is equal to. 0. So we know c is equal to 3. And that's pretty common occurrence, you know, in math class, where it kind of cleans up so that c is equal to whatever the y value is, but you can't always guarantee that that's going to be the case. So particular solution f of x equals ln of the secant of x plus 3. That's a good looking solution right there. Now, most people, you know, just to kind of save themselves from having to do a lot of this work, will just put it on their list of things to do and say, okay, well, I'm just going to memorize that the antiderivative of tangent is the natural log of secant of x plus c. You know, it's not a bad idea. You know, if you put it on your list of things to do, maybe it'll get done. It's hit or miss. Depends. It's all about motivation, but I look at this and I say, well, if I know this fact, wait a minute, I can go from here to here without doing any of this stuff. I kind of like the sound of that, but it does require you to actually know the fact, right? And again, it comes down to like, okay, you got a note card, but if you don't know enough to know when to look at your note card, it's all over. All right, especially for those folks who, and I don't want to assume anything because I think it happens less and less than it used to because of all the times that I go through this spiel in class. But when people say, like right before a test, oh, let me see your note card, and then just start copying down other people's notes off of it, like that doesn't really happen as much because if it did, you're questioning as you're writing it down, like, why am I writing this down? It's not even like this is useful for me. Like, I'm not even going to know to look at this when I need it, you know? So the part of the studying process is knowing what to put on your own note card. And in fact, if somebody wanted to borrow your note card for a test, your thought should be like, why? It's not going to do you any good. It might be a whole note card filled with stuff you already know. These are pieces of information I need to know. You know, it's not going to do you any good. So, you know, take your note card opportunity seriously, and it'll pay off for you. For number 14, I'll set you up with what'll seem like the most ridiculous substitution ever, and then I'll leave you to do the rest, and then we'll take a break. All right. Well, on your own. You know, you don't have to do it here. We're going to find the antiderivative of secant of x dx. Now, I could kind of cut to the chase a little bit. Instead of like taking you down the wrong path, I'll just kind of get you set up with the right one. If you were to write this as 1 over cosine of x, it gets you absolutely nowhere, because you would say, okay, well, my u obviously isn't going to be 1 because the derivative of 1 is equal to 0. That's no help whatsoever. The derivative of cosine is negative sine. There's no sine in there anywhere, so that's not going to be helpful, right? The key to this one, and I'll tell you, this is on my list of things to do. I've been meaning to research the origin story behind this one, but somebody who's definitely smarter than me came up with this idea. It said, you know what? Let me multiply secant by secant x plus tangent x. Then distribute it through to get secant squared x plus secant x tan x over, and I'm gonna write the denominator in the reverse order. Poor quality circle or ellipse. I'm gonna write this as tan x plus secant x dx. Like, why on earth they thought to do that, I have no idea. But they did.
Why wouldn't it just be secant squared x plus tan x? Like, where did you get the extra secant?
Oh, you gotta distribute it through. Because this is a binomial.
Gotcha.
Yeah. Even though it's a fraction, it still acts as a quantity. All right, so what ends up happening is that we are going to create a solution that involves this being the u. All right, but that's where I'm going to leave it. I'll let you try to go the rest of